Hello friends, I hope you're all fine. Today, we'll be diving into Chapter 4 on NMR. Let's begin by exploring the concept of unequal coupling tree diagrams, where we will explore splitting diagrams and tree diagrams in detail. The N+1 rule is applicable only for protons in aliphatic chains and rings under specific conditions. Two main requirements must be met for the N+1 rule to work. All three J values must be the same along the chain, and there must be free rotation or inversion to make all hydrogens on a single carbon nearly equivalent. In typical situations where the N+1 rule applies, hydrogens can interchange their positions by rotating around the CC bonds, making all the hydrogens on each carbon atom equivalent. This results in all couplings along the chain having the same J value. When the J values are not equal, each coupling must be considered independently. This situation requires constructing a splitting tree to analyze the couplings. Let's use these specific values, 7 Hz and 3 Hz, to construct our tree diagram. To construct a tree diagram, start with the largest J value first. For example, with a J value of 7 Hz, two neighbors give a triplet. Each level of splitting uses the N+1 rule. Next, add the smaller splitting value, 3 Hz, to each leg of the first splitting. This results in a triplet of triplets, as each leg of level 1 is split again. When both three J values are the same, the N+1 rule is followed directly. Overlapping legs result in the quintet predicted by the N+1 rule, eliminating the need for a tree diagram. Now, let's examine 2-phenylpropanal, a case where there are unequal J values. The NMR spectrum of 2-phenylpropanal shows different J values. For instance, J equals 7 Hz and J equals 2 Hz, indicating the presence of unequal couplings. Instead of the expected quintet, the methane hydrogen in 2-phenylpropanal is split by two different 3 J values, resulting in a quartet of doublets. Next, we will look at pure ethanol. In an old sample of ethanol, rapid exchange catalyzed by impurities results in a broad singlet for the hydrogen on OH, while the other hydrogens show a quartet and a triplet. In an ultrapure sample of ethanol, slow or no exchange results in a clear triplet for the hydrogens, without the broad singlet seen in the old sample. Graphical analysis is required when different J values are present. For example, two neighbors with J equals 5 Hz give a triplet, while different J values result in a quartet of doublets. Now, let's explore vinyl acetate and its alkene hydrogens. Coupling constants for protons on C equals C double bonds vary. 3J cis is 810 Hz, 3J trans is 1618 Hz, and 2J geminal is 02 Hz. For protons on saturated aliphatic chains, 3J is approximately 8 Hz. The NMR spectrum of vinyl acetate at 60 MHz shows distinct peaks corresponding to the different hydrogen environments in the molecule. Analyzing vinyl acetate reveals that 3J trans is greater than 3J cis, which is greater than 2J geminal, resulting in distinct splitting patterns in the NMR spectrum. Next, we will examine 2,4-dinitroanisole and its benzene hydrogens. The NMR spectrum of 2,4-dinitroanisole at 400 MHz shows distinct peaks for the benzene hydrogens, indicating different coupling constants. Detailed analysis of 2,4-dinitroanisole shows the coupling constants for ortho, meta, and para hydrogens, resulting in a complex splitting pattern. Friends, with this we come to an end of NMR Chapter 4. See you back in Chapter 5 with further studies. Take care, goodbye.